Good morning students, welcome to video lecture class on control engineering. So we'll continue with the problems. The statement is sketch the root locus plot for the system whose open loop transfer function is given by g of s into h of s equal to k into k divided by s into s plus 2 into s square plus 8s plus 20. So we'll begin with the solution. So here the given function is in a standard format, that is g of s into h of s. So no need to modify this one. So k divided by s into s plus 2 into s square plus 8s plus 20. So now we need to identify the number of poles and the number of zeros. So zeros are nothing but terms associated with s in the numerator. Poles are in the denominator. So here if you see the poles, there is one pole, second, and here this is a second order equation, so that if you solve this equation to find out the roots, you will get two roots. Okay, so that means there are two poles for this term. So two for this, one for this term, and one for this. So number of poles is 4, and since there is no term in numerator, k is a constant, so number of zeros will be 0. So now we need to identify the values of poles. So poles are s equal to 0, s plus 2 equal to 0, which will give you s as minus 2. And if you solve this equation, okay, you will get the roots as minus 4 plus or minus 2i. So it is a complex root. That means you are having a complex pole here. So zeros are none. Then if you compare the number of poles and zeros, p is greater than z. So therefore number of root locus branches are equal to p, that is equal to 4. Now you need to identify the number of branches approaches to infinity. So p minus z you need to find out. So p is 4, z is 0. So 4 is the number of branches approaches to infinity. Therefore 4 asymptotes are required to plot the root locus. Once you find out the number of number of asymptotes, you need to identify the angle of asymptotes. For that you are having the formula theta equal to 2q plus 1 into 180 degree divided by p minus z. So where your q value should start from 0. So there are 4 asymptotes. You need to identify 4 angles. So q value will be 0, 1, 2, 3. If you substitute those values, you will get theta 1 as 45 degree, theta 2 as 135, theta 3 as 225, and theta 4 as 315 degree. Then the next step is, once you identify the angle for the asymptotes, you need to identify the centroid of the asymptote. So the sigma equal to real part of poles minus real part of zeros divided by p minus z. So here these are the 4 poles we are having. So from this you need to enter the value of real part of the poles. So real part is 0, minus 2. So here there are 2, minus 4 plus 2i and minus 4 minus 2i. So from them the real part will be minus 4. So here 0, minus 2, minus 4, minus 4, minus real part of zeros, since there are no zeros. Therefore this value will be 0 divided by p minus z is 4. So the centroid is minus 2.5. Then the next step is, you need to identify the RL and you need to mark the centroid and you need to mark the angle of asymptotes. So this is the real axis and this is the imaginary axis. So there are 4 poles, 0, minus 2, and this is minus 4 plus 2j, minus 4 and minus 2j. So there are the complex poles. So if you consider a reference plane here between minus 2 and 0, so towards the right side you are having only one pole, that is summation of poles and zeros you have to take. So it is 1, that means it is a odd. So from 0 to minus 2, it is a RL part. Then similarly you consider a reference plane between minus 2 and this minus 4 plus 2j here. If you take the summation towards the right side, so this is one pole and another pole. So it is 2. 2 means E1. So after minus 2, it is a NRL part, non-root locus part. Then mark the centroid. Centroid is minus 2.5. As I said earlier, it is not mandatory that your centroid must be on RL part. Okay, so minus 2.5 here, and then you need to mark the 4 angles, that is angle for asymptotes. After that, you need to identify the breakaway point. So according to the general prediction, one breakaway point should exist between 0 and minus 2, because breakaway point always will lie on RL part. So to find the exact location of the breakaway point, you need to consider the characteristic equation, that is 1 plus g of s into h of s equal to 0. So where this value he has given, substitute that. You need to simplify this equation to get the equation for k. Here, k equal to minus s4 minus 10s cube minus 30s square minus 40s. Now differentiate this equation with respect to s, then equate to 0. So if I differentiate that one, this is minus 4s cube, this is 3s square into 10, 30s square, and this is 36 into 2 into s, 72s, and which is 40s is there, so differentiation of that one will be 40 to 0. We'll take the negative sign common, so we're left with 4s cube plus 30s square plus 72s plus 40. Now you need to identify the roots for this equation. So if you identify the roots for this equation, directly you can get these roots from the calculator. So one root is minus 0.786 and another is a complex root 3.36 plus or minus 1.2j. So according to the general prediction, your breakaway point lie between 0 and minus 2. So this value lies between 0 and minus 2, since it is a valid breakaway point, and here the real part of this one itself is minus 3.36, that is beyond minus 2, so which is on NRL part, so it is an invalid breakaway point. But if you want to cross verify that one, put this s equal to minus 0.786 in this equation, it is in k equation. If we get this k value as positive, then it is a valid breakaway point. If I substitute that, you will get the k value as plus 13.67, so it is a valid breakaway point. Now to check this one, this minus 3.36 plus or minus 2j lies left to the minus 2, that is on NRL part, so it is a invalid breakaway point. Suppose if you are having this real part as say minus 1.5, for that one again you need to substitute this value in this equation to cross verify that, but here directly we can reject this root as the invalid breakaway point because this part is on NRL. Then the next step is intersection of root locus with imaginary axis. For that you need to consider the characteristic equation, that is 1 plus k divided by g of s into h of s. Simplify that to get this in for this form. So here it is of fourth order. So s raised to 4, s cube, s square, s raised to 1 and 0. So first write the coefficient of s raised to 4, then write the coefficient of s square, then write the coefficient of constant. So conjugative terms you have to consider. Then for s cube it is 10s cube, then write the coefficient of s, then here it is 0. For that, for s square we cannot write this 36 because already I have written here. So now to get this value, okay, this into this minus this into this divided by this 10, we will get it as 32. Similarly here 40 into k minus 36 into 0 will be 0 divided by 40, so it will be k only. Similarly here also this into this minus this into this divided by this term 32, yet and here it is 0 and here it will be, we will get it as k, because if I take this one as a into k minus 32 into 0 will be 0, so here it will be ak divided by this term a, so it will be k only. So now you need to consider the auxiliary equation. So here you cannot equate this k as 0, so I will consider this one. So equate this one to 0, if that is 12 80 minus 10 k divided by 32 equal to 0, so the entire row becomes 0. Therefore from this you will get the k value as 128, that is going to be the marginal value of k. Then you have to write the auxiliary equations. For to write the auxiliary equation, you consider the immediate next row, that is associated with s square row. So it is 32s square plus k equal to 0. Substitute that k value, k marginal as 128. You will get s as plus or minus 2j. So this is the intersection of the root locus with the imaginary axis. After that, so in the last problem we have skipped that 8th step, that is identification of angle of departure or angle of arrival. But here one of the pole is a complex pole. This is a complex pole. So for that reason you need to identify the angle of departure. If you are having the complex 0, that time you have to identify the angle of arrival. So now you need to find out the angle of departure. So for that, on the S plane, first you mark the poles 0, minus 2, minus 4 plus 2j, minus 4 minus 2j. Okay, so I will take this one as the reference point. To this point you join all the poles with a straight line. Okay, and this is going to be your pi p1, pi p2 and pi p3. So pi p1 will be 180 minus this angle. It is a tan inverse of 2 by 4, because you don't know this angle, so you have to take minus this angle so that you will get this outer angle. So to write this one, tan inverse of 2 by 4, because 2 is this one and 4 is the height. Okay, so it is 153.43 degrees is the pi p1. Similarly pi p2 will be 180 degree minus tan inverse of 2 by 2. Here this is 2 and this is 2. Okay, we will get it as 135 degree. Then pi p3 is 90 degree. So pi is summation of pi p minus summation of pi z. Since there are no zeros, so take the summation of these three, you will get 288.43, and angle of departure is 180 degree minus pi. So 180 minus 288.43, you will get it as minus 108.43 clockwise. So for one pole it is with minus sign and another pole it is with plus sign you have to take. Now to sketch the root locus, first on S plane you mark the poles 0, minus 2, and this is minus 4 plus 2j, minus 4 minus 2j. After that mark the centroid at minus 2.5, then draw these asymptotes with respective angles theta 1, theta 2, theta 3, theta 4. After that you have to mark the breakaway point. Breakaway point, valid breakaway point is minus 0.786. After that you need to mark this angle of departure. For this one it is minus 108 degree, and for this one it is plus 108 degree, 108.43 degree. Now to draw the root locus, so the first root will start from pole and it will end to 0, but here there are no zeros, so all the roots will tend to infinity here. So the starting point is the first pole, which is at 0, and it will come to the breakaway point. Then from there it will follow the asymptotes and it will tend to infinity by having the intersection with imaginary axis as at plus 2j. Similarly, the second pole will start from minus 2 and it will come to the breakaway point, that is minus 0.786. From there it will tend to infinity following this asymptotes and having the intersection at minus 2j, and it will tend to infinity. Then the third one is this minus 4.2j, since it don't have the breakaway point, but it will follow this asymptotes having the tangential slope with this 108 degree line. So it will start from here and it will tend to infinity by following this asymptote, which is at 135 degree. Similarly, this this root will start from this pole and it will have the tangential to 108 degree line. Then it will tend to infinity by following this asymptote, which is at 235 degree. Okay, so this is the complete plot of the root locus. After that, the last step is you need to comment on its stability. So if the k value is less than 0, sorry, greater than 0 and less than 180, 128 degree, 128, the system is stable. If k equal to 128 degree, marginally stable. If k is greater than 128, the system is unstable. So here the one extra step which we did today is the angle of departure. This is only because we are having the complex pole there. So here, to identify that angle, you need to take any one of the point as the reference point. For that point, you join all the poles with the straight lines, then you identify their angles, take the summation, then identify the pi value and subtract that pi value from 180 degrees, so that you will get the angle of departure. Okay, so if you have any doubt, you can comment in the comment box. Thank you.